Hello, George Notchik here. In this video I'm going to be discussing how to find the n roots of unity. Unity being number 1. We express it this way. The nth root of 1, that's what we're trying to find. We can express this in this fashion. X is going to be the solution to the nth root of 1. And if we take and raise each side to the power n, then we have x to the n is equal to 1. Moving the 1 over, x to the n minus 1 equals 0. This is a polynomial representation of the nth root of 1. That is, we're going to be looking for those values of x, which when substituted into this polynomial equation, gives us 0. Those values of x that make this vanish are called the roots of 1. And if we confine ourselves to just values of x that are real, there's only one solution if n is odd, and that's positive 1. Putting x equals positive 1, that makes this vanish. If x is minus 1 and n is odd, then this becomes minus 1, where a minus 2 does not satisfy the equation. So there's only one solution in the real numbers when n is odd. But when n is even, we get two solutions, plus and minus 1. For example, the square root of 1 can be plus or minus 1. Because x squared, when x is either plus or minus 1, is a positive 1, minus 1 is 0. So in the real number systems, we only have two solutions when n is even and one solution when n is odd. But we're not going to confine ourselves to the real numbers. In general, the n roots of unity are complex. There's one or two roots that are real, but the rest of the roots are complex. And we're guaranteed, Gauss proved this in his PhD thesis, that if you have a polynomial of nth degree, the roots, there are n roots to that polynomial. If you set that polynomial equal to 0, there are n roots in the complex plane for an nth order polynomial. So, in general, we're going to be looking for the roots in the complex number system. Now I'm going to change my variable designations here. X is usually reserved for indicating a variable for real valued functions, and we use z for indicating variables in the complex plane. So that's what I'm going to do here. We're going to use z to represent a general complex number. So those values of z that solve this equation, z to the n minus 1 equals 0, are called the roots of this equation. Those are the solutions. Those values of z, which when substituted in here, makes this equation true, or makes this polynomial vanish, are called the roots. And there will be n roots in general in the complex number system that will satisfy this equation. That's what we're going to be looking for. Now, this particular polynomial is a special case of a more general problem in finding the roots to an nth order polynomial p of z. In general, we could have some polynomial p of z equal to 0, and those values of z that satisfy that equation are the roots. Now, p of z in general will have a form like this. We could write it compactly as the summation of j equals 0 to n of c of j z raised to the power j. And the CJs in general can be elements of members of the complex numbers. That is, the coefficients here could be complex numbers in general. But we're going to confine ourselves, in this case, our coefficients are just real numbers. 1 in front of the z and the constant coefficient being a minus 1. So we're looking at a special case of the more general polynomial. And I'll discuss a little more about this at the end of the video on some of the theory regarding polynomials and finding the roots. So the question now is, how do we find the n roots of unity? First, it's important to know that an equation of this form has a root at z equals plus 1. We're always guaranteed that. You can see that when z is plus 1 real, that this equation is satisfied. So we're always guaranteed that z equals plus 1 is a solution or a root of this equation. Now, this also tells us then that this equation has a factor z minus 1, is a factor corresponding to the root of plus 1. And what we could do is take this factor and factor it out of this equation and end up with a depressed equation of order n minus 1, one order less than what we started with. And then that equation, we're guaranteed, will have n minus 1 roots, because we have one root at plus 1, and then the depressed polynomial will have the remaining n minus 1 roots, which we're going to be looking for. Now, in the theory of complex variables, it tells us that the roots of unity will be evenly distributed around a unit circle in the complex plane. Now, since z equals plus 1 is guaranteed to be one of the roots, we can use it as an anchor point and divide the unit circle into n equal sections beginning at plus 1. So let's say we're in the complex plane. Here is the real axis, here is the imaginary axis, and here is plus 1. The radius of this circle is unity, or 1. Now we're guaranteed that the roots will all lie on this unit circle that will satisfy this equation, which are the n roots of 1. Now let's say, for example, let's say n is equal to 9. Okay, ninth order equation. So what we have here is z to the 9th minus 1 equals 0, which corresponds to finding the 9th roots of 1. And this is what we want to find. Now, what we do is we start with plus 1 as an anchor point, because we're guaranteed that that root exists in this equation. And then we divide the circle into 9 equal parts. Since n, the order of the equation, is 9, we divide the circle up into 9 equal parts beginning at plus 1. And then those points along the perimeter of the circle are the roots to this equation, or are the roots, the n roots of 1. So what we do then is we just start, we take 360 degrees, which is the total angular measure around the circle perimeter. We start with either 2 pi or, say, 360 degrees. I'll work in degrees here. And since in this case we're looking at z to the 9th minus 1, which corresponds to the 9 roots of 1, we divide 360 by n, And in this case, it's 360 divided by 9, which is 40 degrees. This gives us the angular spacing between the roots along the perimeter of the unit circle. So, the first root is at +1. The next root, we'd move up 40 degrees, go on to the perimeter of the unit circle. That's root number, we'll call this root K. This is K equal to 1, or our kth one root. I'll just call it K1. This is K0. I'll start the numbering with 0. You'll see in a moment why I'm doing that. This is the K2 root, K3, K4, K5, K6, K7, K8. So, we go from +1, we move up 40 degrees, and we get our next root, the second root. Then we go another 40 degrees, that gives us our next root. And we keep rotating 40 degrees to get our roots. So here are our roots, which are evenly spaced around the unit circle, beginning with +1 as an anchor point. So we're done. We found all the roots. They lie on the perimeter of the unit circle, evenly spaced by an angle of 40 degrees, or 360 divided by n, which is the degree of the polynomial, which corresponds to the nth root that we want to find of 1. So we have our 9 roots. 1, 2, 3, 4, 5, 6, 7, 8. There's 9 roots of 1 right there. Now, to find the actual values for these roots, we just use some trigonometry here. Let's say we want to find the K3 root. Well, we rotate from +1 by, we've got 360 divided by n times k. Well, for the first root, k is equal to 0. So we're at 0 angle. The next root, k is equal to 1. In this case, since n is 9, we're dealing with 360 over 9, which is 40. And we multiply that by our k, the step, how many steps we take. So when k is equal to 1, we're at 40 degrees. K is equal to 2, we're at 40 plus 40, or 80 degrees. When k equals 3, we're at 120 degrees. So this angle is 120 degrees. This is for the k third root. Now, let's get the value. We use a little bit of trigonometry to do that, which is quite simple. What we're going to do is project down into a right angle, and we'll call this portion x3, and this side of the triangle is y3. The z3 root can be written as x3 plus j, or iy3, where I is the imaginary unit, square root of -1. The x3 is the real part of the complex number. y3 is the imaginary part. Now, we can see that x3 is going to be the cosine of theta 3, and our y3 is the sine of the angle. Well, the angle is 120 degrees, so our x3 is the cosine of 120. which is minus 0.5, or minus 1/2, and our y3 is a sine of 120, which is the same as the sine of 40. It's positive, and this value is the sine of sine of 120 is the same as sine of 60. Sorry, that's the sine of 60, which is the square root of 3 over 2, or about 0.866 in decimal form. So the real part is minus 1/2. The imaginary part is a positive square root of 3 over 2. So our z3 then, one of the roots of unity is minus 1/2 plus I square root of 3 over 2. That's one of the roots. That's this one right here that we just found. And this corresponds to the factor. If we were to factor it out of this equation, this would be the factor z minus z3. Or this would be equal to putting this in, this would be z plus 1/2 minus I square root of 3 over 2. This is a factor of this equation. Now, in the theory of complex numbers, all complex roots, when the coefficients of a polynomial are in the real number system, in this case we have 1 in front of the z to the n and we have a minus 1, so our coefficients are real. I've proven this in another video that any polynomial that has real coefficients is guaranteed that if you find a root to be complex, there's also its conjugate pair that's also a root. Complex roots in polynomials with real coefficients always occur in complex conjugate pairs. So, let's see what happens. Now, if I found this root, then I've also found this root. This is its complex conjugate pair. We just negate the angle. So, what I could do is I could write this in this fashion. I know that z3 conjugate is also a root. Well, in this case, z6 is equal to z3 conjugate. It's just the conjugate pair. So we would write, so z minus z3 conjugate, we can write this as z plus 1/2 plus I square root of 3 over 2. That is, the real parts are the same between a complex number and its conjugate, but the signs on the imaginary part are opposite of one another. So if z3 minus z3 is 1/2 minus I square root of 3 over 2, then z3 conjugate negated is 1/2 plus I square root of 3 over 2. Now, let's look at what happens when I multiply these two factors together. So I have z minus z3 times z minus z3 conjugate. Expanding this out, we have z times z, which is z squared. And then we have a minus z z3 and a minus z z3 conjugate. So I can pull out the minus z, and I have z3 plus z3 conjugate. And then the last term, I have a minus z3 times a minus z3 conjugate, which is a positive z3 times z3 conjugate. Now, in the theory of complex numbers, I've shown this in some of the other videos, that if we take a complex number and add its conjugate, we get twice the real part of the complex number. And if we multiply a complex number by its conjugate, we get the modulus, or the magnitude, of that complex number squared. Now, all of the roots of unity lie on the unit circle, which means that the magnitude of the roots are all 1. That is, the radius from the center out to the unit circle has a magnitude of 1. So the magnitude of z3 is 1, so the square of it is also 1. So we can put these values in, and we end up with z squared minus z3 plus z3 conjugate is twice the real part of z3 times z plus 1. Now, what is the real part of z3? Well, the real part of z3 is a minus 1/2. That is, our z3 is out here. This is a minus. This is at minus 1/2 is what the real part is at. So putting that in, z3 is minus 1/2. We have a minus 2 times a minus 1/2, which is positive 1. So the equation now becomes z squared plus z plus 1. So that is the quadratic factor corresponding to these two complex roots, a complex number and its complex conjugate. And this happens for all the pairs of roots. If I took k1 and k6, determined its quadratic factor, we're going to have an equation, a quadratic factor with real coefficients. The imaginary parts always drop out whenever you multiply factors involving a complex number and its complex conjugate. I can show that by multiplying this out with the numbers. If I take these two, I have z plus 1/2. Now I'm going to group it this fashion, in this manner. That's this factor, and I'm going to multiply it with this factor. So I've got z plus 1/2 minus, or plus I, square root of 3 over 2. Let's multiply these together. We have this times this term times this term, which is z plus 1/2 squared. Now notice the cross product terms cancel. We have z plus 1/2 times this, minus I square root of 3 over 2, and then z plus 1/2 plus. So these cross products cancel or drop out, and then we have I times I, which is a minus 1 times a minus 1, or plus 1. So we have plus, and then square root of 3 over 2 squared. Multiplying this out, z plus 1/2 squared is z squared plus twice 1/2 z plus 1/2 squared plus square root of 3 over 2 squared is 3 over 4. This becomes z squared. 2 times 1/2 is just 1. And then we have plus 1/4 plus 3/4. So this becomes z squared plus z plus 1, which is the same as what we got there. So we see that the quadratic factors corresponding to a root and its complex mate always gives us quadratic factors that have real coefficients. We can now write down quite easily all the quadratic factors corresponding to complex conjugate pairs of roots. For example, if we take the K1, K6 pair, these are complex conjugates. K6 is a complex conjugate of K1. K7 is a complex conjugate of K2. We just saw that K6 is a complex conjugate of K3, and the last pair here, K5, is a complex conjugate of K4. So we only have to look at the upper half of the roots because the bottom half are just complex conjugates of these. Now, we just determined that the quadratic factor corresponding to a complex conjugate pairs of roots can be written this fashion: z squared minus twice the real part of one of the complex roots times z plus 1. That's a quadratic factor. Well, all we need to do is know what the real part of any one of these roots is, and we can easily write down the quadratic factor. So for example, the real part of K1 is just going to be the projection of its magnitude down onto the real axis, which is the cosine of 40 degrees. The real part of K2 is going to be the cosine of 80 degrees. We're moving up 80 degrees. Real part of K3 we just determined was a cosine of 120. And the real part of K4 will be the cosine of 160. We just increment by 40 degrees as we step along the unit circle. So we can now write down the factors corresponding to, we have z to the 9th minus 1. Well, we know one root is at z equals 1, so that factor is z minus 1. That's the only real root. And then we can write z squared minus twice the real part of K1, which is the cosine of 40. So we could write this as twice the cosine of 40 times z plus 1. I'll just write that. And then another factor would be z squared minus twice the cosine of 80 times z plus 1. Then we have z squared minus twice the cosine of 120 times z plus 1. And the last one would be z squared minus twice the cosine of 160 times z plus 1. And if you were to expand this out, you would end up with z to the 9th minus 1. This is a 9th order polynomial. We have z squared, z squared, z squared, z squared, so that gives us z to the 8th times z to the 9th. So if you did all this expansion, you'll find that terms dealing with z to the first up to the z to the 8th will all drop out. So we can easily write down our quadratic factors just by knowing the real parts of the particular roots, and we only have to find 4 of the roots because of the complex conjugate pair nature of the way that the roots appear in on the unit circle. Let's try another one. Let's do a fourth order. Find the four roots of unity. So what we're going to do is find the four roots of unity, which can be written this way. Remember that the four roots of unity is equal to z. We can raise each side to the fourth power, so we get 1 equals z to the fourth, and then we subtract 1 from each side. We end up with this equation, this polynomial. Now, again, we start with our anchor point at +1. We know that root exists. For any equation of this form, regardless of what the power is, we're always guaranteed that one of the roots is at +1. So we'll start here at +1. Now, we need to determine the spacing between the roots. We do that by taking 360 degrees and divide by the power. So in this case, 360 divided by 4 is 90. So we know the roots now are going to be spaced equally on the unit circle with 90 degrees between them. So if we go 90 degrees from +1, that puts us up here at +j. We go another 90 degrees, that puts us at -1. And we go another 90 degrees, that is at -j. So those are our roots. The roots for this equation, or the four roots of unity, are going to be z0 is +1, z1 is I, or j, I keep interchanging. Mathematicians use I, electrical engineers use j. I'll try to stick with the math convention. Z2 then is -1, and Z3 is equal to -I. Now notice again, if we have a complex root, we also have its conjugate as a root. I and -I are complex conjugates. So this corresponds to factors of z -1 for z0 times z +1 for the -1 times z -I for the z1 and z plus I for the z3. And if you multiply this out, this should be equal to z to the fourth -1. Multiplying that out. We can easily see that if we take this pair and multiply it. Z times z is z squared. Cross product terms drop, and we end up with a -1. On this one, we have z squared. Cross product terms cancel. They're opposite. Then we have -I times I. I squared is a -1 times minus, so it's a +1. So now we have z squared -1 times z squared +1. We multiply them together. Z squared times z squared is z to the fourth. We can see the cross product terms cancel, and we have a -1. So indeed, this is equal to z to the fourth -1. Now notice that with an even root that we're trying to take, we end up with two real roots, one at +1 and one at -1. Whereas when the power was odd and we're taking an odd root, we only end up with one real root. We don't get -1. This is always true. On an equation of this form, where we have z to the n -1, where we're looking at the nth root of 1. If n is even, we end up with two real roots, one at 1 -1 and one at +1. And if n is odd, we only have one real root at +1. And this is always the case. So that's how we find the roots of unity. Now I'll go ahead and talk now a little about complex number theory and how this all came about. Here we have the complex plane. I have the imaginary axis and the real axis, and I've drawn a unit circle about the origin. That is, every point on this circle is a unit distance away from the origin. So if I pick, say, some complex number z on the unit circle, the distance, radial distance from the center out to that point has magnitude 1. And then we have an angle corresponding to that complex number. So we can represent this complex number two ways. We have the rectangular form, which tells us that we have x plus I y, where x is the real part, y is the imaginary part. And we can also represent this in polar form, where we have the magnitude, or exponential form, the magnitude, which is 1 times e to the I theta z. This is Euler's identity. And we can represent this in polar form as 1 at an angle of theta z. We're going to be interested in looking at it in the exponential form. Now, notice that with the angle z, it isn't unique representation. If we wanted to represent z, there's an infinite number of ways that we can represent this very same point in the complex plane. All we have to do is add 2 pi to the angle. So if we start here and go around 2 pi, or start here and go around 2 pi, we end up at the same place. Or we can start here, go around once, twice, 3, 4 times. Any integral number of complete turns around gets us to the same point. So we can represent the angle in the following manner. Theta z, we can add to it integral multiples of 2 pi to theta z, and we end up in the same place. So we could add 4 pi, 6 pi, 100 pi, 1,000 pi, as long as it's an integral number of 2 pi's. So when we look at the nth root of z, or of 1, z is going to be the nth root of 1, which corresponds again to the equation. If I take each side to the power n, I can get rid of the radical and then subtract 1 from each side. And this is the polynomial equation corresponding to the n roots of 1. Well, 1 can be represented in this fashion, where theta z is equal to 0. Positive 1 is right here, where theta z is 0. So we can represent 1 in this fashion as e to the I 0 plus 2 pi k, where k is an integer. So I'm going to put that in here for 1, and I will rewrite this rather than in radical form. This is 1 to the power 1 over n. Well, 1 is e to the I 2 pi k raised to the 1 over n power. And using properties of exponents, this can be written as e to the I 2 pi k divided by n. So z equals e to the I 2 pi over n times k. And what is this? This is the angular separation between the roots. that we determine is that you take the power, you divide it into 2 pi or 360 degrees, and that gives you the even spacing between the roots on how they lie on the unit circle. So as we increment k, k goes from 0, it's an integer, and it goes all the way on up to n. When k is equal to n, we're back to where we started. That is, we're starting at plus 1, and when n is, or k is equal to n, we're back to where we were. So there are, there are n unique roots. If we start at k equals 0 and take it up to n minus 1, that gives us all the roots. And then when k is equal to n, we're back to where we started at plus 1. So there are n unique roots as we increment k from 0 to n minus 1 on this equation. And this gives us the roots. And we can get the real and the imaginary part by using Euler's identity. E to the I 2 pi over n times k can be written as the cosine of 2 pi n times k plus I times the sine of 2 pi n times k, and we increment k is equal 1, 2, 3, and so on up to n minus 1. So that gives us all the roots of unity. We get n unique roots as we increment k from 0 to n minus 1. And we're always guaranteed to have one real root at plus 1. Now, depending upon whether n is even or odd will determine whether or not we pick up the root at minus 1. If n is even, we pick up the root at minus 1. If n is odd, we only have plus 1 as the real root. Now remember that in this sort of equation, since we have real roots or real coefficients in the equation, then any complex roots of unity must occur in complex conjugate pairs. I proved that in an earlier video. And so if zk is equal to xk plus iyk, then we know that zk conjugate is also a root, so it would be xk minus iyk, the complex conjugate. And since all of these roots must lie on the unit circle, there can be at most two real roots. The circle only intersects the real axis in two places. So at most, in this equation, regardless of what n is, there can be at most only two real roots. And if n is odd, the two real roots are plus minus 1. And if n, if n is even, the roots are real roots are plus minus 1. And if n is odd, there can only be one real root. Now the reason you can reason that is since roots have to occur in complex conjugate pairs. If n is odd, we know we have at least one real root. We have plus 1 as a root. So then if we take that away, then the number of remaining roots is an even number. We start with an odd number of roots. Plus 1 is one real root, so the remaining roots number an even number. Well, since roots have to occur in complex conjugate pairs, there can be no other real root because we have an even number of roots remaining and they have to occur in pairs, so that uses up all the values in the even number of roots remaining. And if the n is positive, or is even, then complex conjugate roots have to occur again in pairs. If n is even, we know that plus 1 is guaranteed to be a root. So then, taking that away, we have an odd number of roots remaining. Well, we cannot have a lone wolf in the complex conjugate pairs. If, say, n starts out as 9, we take away the real root, we're left with 8 remaining roots. Well, one of them cannot be real, because that would leave an unpaired root. And there at most can only be 2 real roots. So we can't have an unpaired complex root, because they have to occur in complex conjugate pairs. So if n is odd, then we at most can have 1 real root, which is plus 1. Now, one last thing I'm going to do here is let's prove algebraically that if if one of the roots is 1, is plus 1, that is, z equals 1 is a root, then there's a factor z minus 1 corresponding to that root. Now, it must divide into this equation without a remainder, z to the n minus 1. If we divide that factor into this equation, it must do so without remainder for this, because we know that this is a factor. So if we look at this, if we multiply, do this division, take z n to the minus 1 times this becomes z to the n minus z to the n minus 1. We subtract, those go out, we have zn minus 1 minus 1. So then we have zn minus 2. This becomes zn minus 1 minus zn minus 2. We subtract, we get zn minus 2 minus 1. You can see what's happening. The next one will be zn minus 3, and this will go on down to 1. So this is interesting. What happens here is we see then that the depressed equation, when we factor out the z minus 1 corresponding to the real root at plus 1, we end up a depressed equation, polynomial of order n minus 1, where all the real coefficients are unity. So the claim here is that is z minus 1 times z to the n minus 1 plus z to the n minus 2 plus z to the n minus 3, so on as we go on down. Is that equal to z to the n minus 1 if all these coefficients are unity? Okay, well, let's look at it. I'm going to write, if we look at, if I take, I want to know if z to the n minus 1 is equal to this factor, z minus 1, times the depressed equation, which is going from j equals 0 to n minus 1 on z to the j. That is, if we expand this out, what I have here is with j equal to 0, we have z to the 0 Expanding this out, z to the 1 plus z squared plus z to the third, and so on to z to the n minus 1. So this is the compact summation that represents this depressed equation where all the coefficients on the terms of z are unity. So we want to know if this is equal to this. Well, let's expand this out. We have z times the summation, so we have z times the sum, j equals 0 to the n minus 1 of z to the j minus 1 times the summation, or the summation j equals 0 to the n minus 1 of z to the j. Now I'm going to work on this, and what I'm going to do is I'm going to take and notice that at the last term we have z to the n minus 1 in the summation times z, so that is z to the n, and I'm going to add to that what's left on the sum, which is j equals 0 to n minus 2 of z to the j. Let's convince ourselves that this is indeed true. And what I've got to do here is, since the z is multiplying through, well, let me back up here so I don't confuse you. Let's multiply this out. I'm going to bring z in time into the summation. So we got j equals 0 to the n minus 1 of z to the j plus 1. And then I'm going to subtract off. I'm going to drop the initial term where j equals 0. So I'm going to start the sum at j equals 1. And we're going to go to n minus 1 of j to the z. And the term corresponding to j to the 0 is just minus 1. When j is 0, we have z to the 0, which is 1. So I've just pulled that out of the summation, and I'm starting the sum at 1. Now, let's look at the first sum. Well, I'm going to pull out the last term of the sum, where j is equal to n minus 1. And then I'm going to stop the sum at j equals n minus 2. So when j is equal to n minus 1, we have z of n minus 1 plus 1 plus the sum of j equals 0 to n minus 2 of z to the j plus 1. I've stopped the sum one term sooner than what I had up here, and I pulled that last term out. We have n minus 1 plus 1. The 1's cancel. That's z to the n plus this. That's equal to this sum. And then this is the other sum. Now, let's look at this sum here. Let's change our indices. I'm going to let r equal j plus 1. So when j is 0, r is equal to 1. And when j equals n minus 2, putting n minus 2 in here, r is equal to n minus 1. So I'm going to change the sum, the dummy variable, inside the sum. Instead of j, I'm going to write it in terms of r. So that's r equals 1 to n minus 1 of j to the r. And then we have this sum minus the sum of j equals 1 to the n minus 1 of z to the j minus 1. Well, look at these two sums. These are identical. The only thing that's different between them is the dummy variable of summation. But these are exactly the same sums, and we're subtracting them. Convince yourself that this sum and this sum, that goes to 0. They cancel. So we're left with z to the n minus 1, which is indeed what we started with. So again, we know that we can factor out the root, the factor corresponding to this root, and what's left with is a depressed equation where all the coefficients are 1. So for example, if we're finding the 6 roots of 1, we're finding all the z's that satisfy this equation. We can exponentiate both sides of the equation by the power that we want to have the root at. So we take the 6th power of each side. So we got z to the 6 equals 1, or z to the 6 minus 1 is equal to 0. We want to find all the z's that make this true. Now we are just showed that we're guaranteed that one of the factors corresponding to the root z equals plus 1 can get factored out of this equation, and what we'd be left with is a depressed equation of 1 degree less where all the coefficients are equal to 1. So we have z to the 6 minus 1 equals 0, and this can be written as z to the 5th plus z to the 4th plus z to the 3rd plus z squared plus z to the 1st plus 1, and that's equal to 0. This is the depressed equation of 1 degree less than what we started with, and all the coefficients are equal to 1. Suppose we have z cubed minus 1. Well, we can write this as z minus 1 times z squared plus z plus 1. And we're guaranteed that that will be equal. Again, you can see that if we multiply z through on this equation, we have z times z squared, which is z cubed. Z times z is z squared. Z times 1 is z. Then we have minus 1 times z squared, which is minus z squared. Minus 1 times z is minus z. And minus 1 times 1 is a minus 1. The z squareds go out. The z's go out. We're left with z cubed minus 1. So this is always true. The depressed equation are just powers of z with coefficients equal to 1. This video ended up being much longer than I first intended. However, I think we've pretty well killed the problem of finding the n roots of 1. If you understood everything that went on here, you should be able to very easily generate any number of roots of 1, whether it be the 6th roots of 1, 10th roots, or 20th roots of 1. All you have to do is find the roots, the real parts of the roots in the upper half of the complex plane. And the way you determine those roots is you start at plus 1 in the complex plane, and if you want to find n roots, you take 360 divided by n to get the spacing between the roots, and then you just go around the unit circle, spacing the roots by, say, this theta k. Each root will be spaced from the other one, previous root, by the same amount. You go all the way around. You only have to consider the roots in the upper half plane, get the real parts, and you can, from these, create quadratic factors, or write down these roots immediately and then take their complex conjugates to get the other half of the roots. And it's a very easy way to generate the nth roots. of 1. So that wraps it up. And